Hi, my name is Michael Hansen. I'm a master student in astrophysics at the University of Copenhagen, and I would like to show you how to do basic image reduction in IRAF, or as I will use for this session, PyRAF. It is essentially the same, other than PyRAF has a more nice guided user interface than the original version of IRAF has. Obviously, in order to do this reduction, you need to have some prerequisites. Sorry for my English, it's not my native language. But, anyways, you need to, of course, have some data. In this session, I have borrowed some data from one of my fellow amateur astronomers. He has gotten some data from the cluster Able 2218 with iTelescope, which is an online telescope. You can log on, pay some money, and then you can take some images of whatever you want. There are telescopes all over the world, so and then I would say that at any given time you will have a telescope at your disposal. Of course, if no one else is using it. So for this session, we will have luminance and red, green, and blue filters. Now, usually for scientific data, you'll be using something like, let me show you this, I have it here. This is some what I've gotten for myself. You would have, usually you would take something in BRV or UBV filters. This is standard photometric filters. But for this session, I'll be using red, green, and blue, normal filters used for color imaging, basically, and the luminance filter in order to get all the details. Now, this session is going to be a little special because, as you can see, I have bias 1x and 2x and dark 1x and 2x. This is for 1x1 binning and 2x2 binning. It's just my shortcut for it, and this is the same. Now, for the filters, the color filters, you have flat images. But because iTelescope doesn't provide any raw filters, then this is a master flat filter, master flat image that they have made. But in order to show you how to combine your flats, I'll be doing this luminance flat here, where I have deleted the master flat in here. So I'll show you how to combine this into an actual master flat, but I'll not be using these flats because I'll be combining this red filter here. I'll show you how to do that. So you need to have actual data, luminance, red, green, blue here. Then you need to take bias frames, dark frames, and then flats, as I have put in all these directories in here. And then I have this little Python script that I will explain a little about when we get to that. But basically, first, this is the data you need to have. Also, you need to have IRAF or PyRAF. Now, like I said, I'll be using PyRAF, and there's a neat way to get this. As you can see here, you just log on to the SSB, this address up over here. If you search for Eureka and Space Telescope, then you'll probably get somewhere to this page. Then you'll download the installer, run it like this, and then type setup. Now, if this doesn't work, then you can find help on this page. You need to run another script in order to get this setup. And of course, when you have this setup, then you will need to do this every time you want to run PyRAF. But because obviously you don't want to do that, then there's a little thing you can do. Now you log on to a terminal, and then you go into your home directory, and then you can say pico.bash rc. Sorry, this is of course something else if you don't use bash in your Linux setup. And then at the bottom of it, you just type UR setup. Now every time you start a terminal, then it will be running this UR setup, and you'll have PyRAF at your disposal. So this is a nice way to do this. Third of all, sorry, for this tutorial, of in order to do this with me, or when you have seen this video, you need to have some sort of tool to manipulate arrays. Now I'll be showing you how to do this in a program I'd use at the university called MATLAB. This costs a lot of money, but you can also write a Python script or anything you like to do this calculation. It's not very hard. All you need to do is know how to write a script or a program that can load in some data and then manipulate these arrays in this data you have loaded, and then output it somehow, either to a file, or as I do here, just copy it to another text editor. But I'll be showing you how to do this later. So let's get started. So first of all, we want to have a terminal open. Now I've made a little bash script, or whatever you want to call it, that can help you when you start up your program. But what you basically would do was to type ds9. That is put in the Eureka package, so you don't have to worry about installing it. Do this, press enter, and then you would open PyRAF by typing this command. Now I have made a little script where I can type PyRAF in order to do both at the same time. So here you get ds9 open, and then PyRAF will load. So here we are. Now I will usually be removing this color bar down here like this, and then also be removing the buttons, sorry, in order to get a little bigger view place. Now of course we are here, and I have put all these data files in a portable drive, so I'll just be going there. Alright, so here we are at the same directory that I showed you before. Now what we want to do now is to combine the bias 2x and the dark 2x, and we want to do it in these steps. And the last step would be to combine the flats. Now again, I want to remind you that I'll be combining bias 2-bit and dark 2-bit, but the flats in the luminosity directory, which I have the raws for, are in 1x, but are bin 1, and but that's basically the procedure is the same. You just have to choose different files. So let's go into the bias 2x library and look what's in there. Now we have some data and we have a log file. Now there's actually not much to be doing here, but you'll need to know some basic IRAF commands. So you can say lpar. This stands for list parameters, and we'll be using something called zero combine. This is for combining zero images or flat bias images, as we have here. Now you can see that the different parameters in there. Another is called epar, edit parameters, which we'll be using here. And then I'll just move this out of the way and make it a little bigger. Now, if you were, I can do that. If you were using IRAF instead of PyRAF, you'll get this image would be looking more like this, and you'll edit it with another text files and do it in there. but I find that the PyRAF environment is a little a little nicer to have. And furthermore, using this Eureka package that I got, you'll also get the combining program called Drizzle Pack for the Hubble Space Telescope, so you could basically download your own Hubble images and then combine them to get pretty nice data. I have used this a number of occasions now in order to get data for my for some models I've made that I can make a video about later. But let's get started with this this combining of the bias images. So let's take a look at the parameters we need to change. Now, all of this you basically don't need to change, but if you want to, you can choose the combining method and the rejection method. Let's take a look up here. You have the input. Now you can do it in many ways. You can make a list. I'll show you how to do that. So you'll take a look again. Is what is in here. We have a lot of fit files. That's because it comes from MaximDL. They don't call it fits. They call it fit, but it doesn't matter. It's basically the same format. So you'll just type files. Use this wildcard down here. This. And then if you do that, you just get a list. You can't do anything about that with that. But if you just pipe it or send it into, let's call it input, then you can show that you have this little file here. And lucky enough, if we edit the input file, we will see, when my computer gets there, the list of files we have to edit. That's nice. So let's open zero combine parameters again and take a look. Now, if I have just used the wildcard.fit, but now we have made this fine input file, we'll just use this add input. It's basically the same, but of course using wildcard.fit takes every fit file in your directory. But if you change the content of the input file, remove some images or whatever you want to do, and use this instead, it'll of course only use the images that are in the input file. Then we have this output. We want to output it to, this is the name you want to give it. I call it bias underscore master.fits, but you can call it master fits bias, whatever you want to call it. It's just a name. Now, this is the combining method you want to, this is how you want to combine your images, basically. There are some average or median. I always use median. And then there are some rejection types. You can use none, min-max, CCD clip, CR reject, C clip, blah blah blah. So go on. Now, you can use, I would basically use sigma clip and then change the low high sigma down here, or I will be using the CCD clip. Now if you're using the CCD clip, there are some things you need to know. You need to know the readout noise of your detector, and you need to know the gain of the detector was used. Now unfortunately, these were not provided by neither the manufacturer of this detector used or wherever you look for it. So I had to calculate it myself. Sorry. If you want to do that, there is a IRAF command called find gain that you can use. For that, you need to have 2 flat frames and 2 bias frames, and then you can do it. It will of course be an estimate, but it will be rather okay to use. So now we have put all our parameters in here and what we want to do, and then we'll just press execute, and then it'll be running. So let's take a look, and we have a bias master file. That was easy enough. So we'll go back. Now we want to look at the dark. So we'll go into look at the dark 2x, and we have a lot of dark files in here. And I'll be using the wildcard this time. But again, this time we want to do something else. So we will go into something called ccd-proc. Now there are many ways you can do this. You can also create a little script and then use a command called imirith. Sorry, can't spell. Imirith, where you can basically add, subtract, divide, or multiply images together. You can multiply images with numbers. You can basically multiply anything with anything that you can imagine related to astrophysical or astronomical data. So that's the basic. But ccd-proc, processing of ccd-proc, is a little easier to use. So let's take a look what we have in here. Now we have used input, that's from another session. But one thing we have to be absolutely sure about what we're doing here is that we go in and change this. I'll be using the .fit wildcard, and we'll call it temp1. No, I have already made a file down here. You can see dark, so we'll just say dark. And this is another thing, a little trick you can do. You call it temp1 because it's temporary, backslash, backslash, bar, whatever it is called, add dark. Now what this will do is that it will add this temp1 in front of whatever is written in here in the dark file. Now this part ccd type is if you have actually a parameter in your fits file header which tells what this kind of image is. So if we had a dark in there, we'll just write dark. But since we don't have this in this kind of fits file, we'll just delete it, so it just change. If I would have written anything in here that wasn't present in the fits header in the files, it will error. It wouldn't run. So there's a lot of parameters down here that we can take a look at. If you want to list the processing steps and not do anything, we can take this. We won't do that. Fix pics, we won't do that. We won't use overscan because we don't have it here. And we won't trim the images. These are the important parts for this session. So we have zero correction. This is bias. We have dark correction. This is dark. And we have flat correction, which, well, surprisingly enough, is flat. So we have only, let's assume that we haven't done any work, previous work. So what we have here is only bias. So we'll just unclick this. Now what we want to look at again is this. We won't be using this trim section or anything, but we have zero, dark, and flat. Now if we, let's assume that we hadn't done anything here, so I'll just delete anything, delete everything in here. So this is what it would look if we hadn't done anything, which we haven't. So we'll go in here, and then you could write the name here, the directory, the path for the file. But PyRAF has another very clever mechanism. You just right click, and then you get an ability to select the file you want to use. Now we wanted to combine dark to bin, so we will have to correct for bias to bin, the file we just created. And we'll just open that. And this is all we need to do because we haven't gotten anything else. Yeah, just press execute and let's see what happens. So let's take a look what's in there. We have dark, we have these temporary files out here that we asked it to make. So what we'll use now is task called dark combine. It's actually very easy to figure out. So I've used the wildcard option here. I will call it dark master. I'll be using the median combine method. I'll be using CCD clip. And again, I have set the read noise and the gain. The sensitivity noise I haven't found anywhere, so I've just set it to 0. And we'll be scaling the images according to exposure, but you could use none, mode, median, whatever you want to use. I find that exposure is the best for this kind of image. So we'll say execute, and we get an error. So let's see why we get that. It says no images to combine. Let's see here. Yeah, maybe I know why. No. That was strange. Alright, so I suppose I figured out what the error was. So I've gone back to this the CCD processing again, same settings, and then press execute. Now the problem was that I apparently had these temporary files again. Now one thing you need to know about IRAF is that if you have images like this temporary, like I've called them in advance, they are still they are here, and then you do this processing or whatever you are going to do on them again, then it will not overwrite them, it will simply add them to this fit file. As you can see here, it says that you need to tell what fits extension you would be using, and this means that if you have an image with more with more data in it, several images or more fits headers or whatever it is you want to use, then you would be calling it, let's just say that I want to display temporary 1 1210, yeah, so this is correct. Fit. I'll explain these commands later. Now, if I wanted to, if this had more in them, I would be using this command like this. It can't do that because it's not there. Then I will put say 0. Then we'll be showing it, or 2 or whatever you want to. It can't do that because it's not in there. But the other images that I had, if I had done this with 1, it will be showing me an image. So let's try this again. This is, again, if you want to see it, this is the dark image that we have, that we have corrected for bias now. This is the bias corrected image, and then we will be combining these to a master dark file. So we'll use this dark combine again. Now one thing you sort of maybe should remember about IRAF or PyRAF is that you don't actually have to write the entire name, but it has to be unique. So if there are more programs or tasks, as it's called in IRAF, that has this extension, then it won't be doing it. But because there's only one dark combine comp, then it will show me the task. So the same settings again, CCD type nothing, scaling with exposure and setting the read noise and the gain from the detector, and let's say execute and see what happens. Yes, so let's take a look what we got. We got a dark master. So let's try to display it, dark master. Now this one here, let me explain what this does. Now this is a display task in PyRAF or IRAF. So what I want to do is you can and also here you can go in and say EPAR display, and then you'll get this with a lot of things you can change. But basically what you also can do is you can let's say LPAR display. So these parameters in here, B mask, whatever you want to have, you can see I have something called set scale here, and somewhere else that should be set range. Yes. Now, and you have a set 1 and set 2 here. Now these parameters you can go in with the edit parameter EPAR and change them there. You can write display, let's say dark master fits. Now the one number here is the frame you want to be writing this to, and if you look at IRAF you can make a lot of frames in here. Of course, let's see, I have a frame 1 here, so let's just say I want to show it in frame 2. One thing you need to know is that if you want to change a parameter, you can set range equal to yes, and set scale equal to yes. Now this will work, but the shortcut is to write set RR plus, set RA plus, and then set SC plus. It will do the same. So let's see. So this is the master dark that we have, and as you can see here, we have 2 frames. And you can do this. You can put many frames in there. Actually, in here you can change how many threads you want to use also. So I think that DS9 has a maximum of 16 frames to use, but I'm not sure about that. You can look it up. So now we have combined the dark. We will have to change a little of what we are going to do. So we'll go into the luminance and look into the flat directory. Now again here I want to delete the temporary the temporary files. Just write failure. This is what we start out with. So first we will do the same as we did with the dark. We'll go into EPAR and we'll use CCD processing, and this time we'll say, well, we have a flat because we have the flat file down here, and we'll write this as flat again. We'll change that. Now we have a dark file, so we'll be using dark correction. Now because these flat images here are for 1x1 binning, I'll be changing this, but be reminded that it is basically the same procedure. You'll have to combine the bias and then correct the dark images with the bias master you have created and combine them, and then finally you'll have to combine the flat images while correcting for bias and dark current. So let's change this and go to bias 1, and then take the bias master, go in here and take the dark one and take the dark master, and of course we haven't got any flat, so we won't be correcting for flat, and this should do it. Yes, let's try to say execute. If you were using IRAF instead of PyRAF, you can, when you are editing the parameters, you can press :.go and then enter, and it will be sort of the same as pressing execute in PyRAF here. So we'll just be waiting for CCD proc to getting finished. This is writing to an external hard drive I'm using, so this is the reason why it's going a little slow, but let's see. Yeah, now we got the temps here, and we'll be using, not surprisingly, a task called flat combine. So let's take a look. Sorry, what's in here. Now we have the temporaries here, as I've used here, with the wildcard. But then there's something else here, the temporary flat. I'll call it something else. I'll explain to you in a minute why I've done that when we have combined these. But other than that, median, CCD clip, set the read noise and gain like before, and then I've chosen a little window to use statistics because I'm scaling in using mode. Yeah, and you can use whatever you want to, median, mean, exposure, but for flats I find that mode is the best way to do it. And you can also use you can use sigma clip and then just check with these low high sigmas, or use something else. You can use low and high, min max. These are changed here. This is basically how you want to reject bad pixels, or you want to refine your image, but I find that CCD clip is pretty good in this regard. So let's say execute. And it is running. So now we have this temporary flat here, this one. When you're dealing, let's just, for the sake of it, show it, display temp flat dot fits in the one set yeah. So here we have it. This is the flat. Now just a basic introduction to why we are actually doing this. When you are taking images with a CCD recorder or camera of any sort, that is not using film but actually using sensors like this kind, you'll get a couple of noise, or whatever you want to call it, artifacts in your image. So the bias is actually when you have this CCD recorder, in order to get an sort of even input, we actually provide a bias offset on the recorder. Now, in order to take care of that, in order to not have this bias offset in our data, we take a lot of zero exposure images and then combine them. This is the bias. Now, the dark frames are not typically used on professional cameras because they're usually cooled with helium or nitrous oxide or something like that. But flats they do use. Dark images is when you have this CCD recorder. If you haven't cooled it enough, it will create dark current. It's from the electronics itself. And in order to reduce the artifacts from this, you take a lot of exposures where the recorder is blocked out, so it doesn't get any light from the telescope, but the exposure time is the same as your light frames or your science frames. So in this particular case, the science frames is 300 seconds exposures, so the dark frames has to be 300 second exposures as well. And we can actually check this. We can use the command of the task called hselect. Then we'll just take one of the temporaries, one luminous, let's say 01.fit. They should do it, and then we'll use this wildcard in order to get the names. Then we'll say x time and yes, and it will show us that the exposure time for this luminance flat frame is 1.977 seconds, but I'll show you later that the science frames is actually 300 seconds. I can show you now. Let's go into check the, let's see the dark. Let's just take the 1x, and then we'll show H select dark master fits, the same as we did before, X time, yes, and then you'll see that the exposure time is 300 seconds as the science frames are, or the light frames in this particular case. So now we are back at this part here. Now the flat frames is because, as you can see here, actually we have a lot of dust specks now. Let's just go back a while and no, wait a second, sorry, it's a bit late here. It's 20 minutes past 1 a.m. so I'm a little confused now. I seem to remind that I have the dark frame, yeah, here. So this is the dark master that we made. Now all these white specks here, all of this is dark noise on the imager, and you can see there are a lot of them in here. Now this gradient over here and the streaking from here is an artifact from the way the sensor, this particular sensor, is read out, but the dark reduction should also take care of this. But these little specks here are what you call dark noise. So let's go back to the flat frame. So the bias frames are 0 seconds exposures. Now most cameras can't take 0 second exposure, so you usually use the lowest exposure time you can practically use on the sensor. It could be 0.0001 second or something like that. And the dark frames like these have to be the same time as your science exposure. So if your science exposure is 600 seconds or 300 seconds, your dark exposures have to be 300 seconds or 600 seconds. Now, how many you need to have is dependent on your chip. I would say for a cooled, good chip like SBIC Instruments or Starlight Express, you could probably use about 10 dark frames, maybe 5, but 10 is the most secure. If you're using DSLR or, well, to be honest, lower quality CCDs that are not so well cooled, then probably something around 20 dark frames. The problem, of course, with dark frames is that your exposure time has to be the same length as your science frames, so it could take a lot of time if you have to make a lot of dark frame exposures. Now the flat frame is a little trickier, because this is actually an exposure through the telescope against something that is evenly illuminated. It could be a white surface, or as many professional telescopes do, they actually take twilight flats. There are many guides to do this on the internet. I won't be going deeply into how to do this, but you can see all these little dust specks around here. This is from the mirrors in the telescope, and this is called dust donors. This is actually artifacts that are placed on the telescope, on the filter, on the chip, wherever you can use it. Now this is a luminance, so of course there's no filters here, but it could be, it's anything that is in the light path from it enters the telescope till it gets to the CCD, or actually get read out, because there can also be things on the artifacts on the CCD window itself, but it's what the flat do. Now the exposure for these flats doesn't have to be long, but it have to be that the average value on your, you can see it up here, this one here, it will have to be somewhere around 30,000, maybe 20,000. I don't think there's really any um, what you call it, agreement of how long it should be, but we can use one task called imstat or imstatistics on the temporary flat and just take a look. So it shows you the number of pixels, the mean value, the max, and the mode. Now you can see the mean, it's around 31,000. So this is what you want to aim for. The most important part of the flat frame is that it must be evenly illuminated. Not the flat frame itself, of course, because it's dependent on the light path or the telescope and the CCD you're using, but what you are recording at the end of the telescope have to be as evenly illuminated as you possibly can get it. And flat frames you'll need about 10, 15. I think we have 20 here, so it's sort of a good number. Now, this is what was a little detour, but I think it was very important. But what I wanted you to tell you about now, and what I actually needed to use the statistics for, is that, as you can see, all of these pixels have some value. You can see it here, a pretty high value. Now, when you reduce data, you subtract bias and you subtract dark, but you divide by flat. Now, if you divide some number by a large number, it gets smaller. If you divide a large number by a very small number, it's still very large. So what we want to do here is to correct for changes, imperfection in the CCD, and of course this what's in the light path. We don't want to subtract a lot of light information out of our image, just correct for the differences, the gradients, as we could call it. So what we want to do here is, and I'll show you how it works, and that it actually works. So to be sure, to be precise, it's a difference we want to correct. It's not, you can see it this way: if I divide an image by a difference with a very, very large value, the difference will be the same. If I divide an image by I have corrected for the difference, of course. If I divide an image by a gradient, or an image with the same differences but with a very, very small number, I have still divided by the differences, corrected for the differences, but I haven't pulled out so much data from the image. Now, if you're doing what some people call pretty pictures, then this will not be very important, because you can just correct it when you scale the image. But if you're doing photometry, simple photometry, then it is very important that you divide by a flat that is as small as possible, because other than that you'll actually pull lumens out of your image, of pixel pixel values. Now, you can see it this way, that when you do photometry, you're actually counting photons. So photons get converted to a binary number that is a value on the pixel, as you can see it here, this value. And if you divide it, then you take pixel values out and you actually change the luminance of your image. And this will give you an offset of the photometry. So in order to correct for this, we'll use this mode number here. Now I'll be lazy and just copy it. And then I'll be using this I told you about before, this image arithmetic, imarith. So we'll be dividing the temp flat dot fits. See if you can find it. No, I couldn't. Divided by the mode number dot 0, and this I will output as the flat master dot fits. So let's try to display the flat master dot fits at let's see, what frame is this? It should be 2. Let's put it in 1. Sorry, There was something wrong here. Oh, it's here. So now I should be able to have the other frame. No, sorry, no. But as you can probably remember, all the pixels around here on the image had some certain values, about 30,000 pixel values, ADUs, as it's all called, analog to data. But here it has values very close to 1. So you can imagine, and let's do the imstat on it. Imstatistics, flat, master.fits. As you can see, the mode is 1 and the mean is close to 1. So you can probably imagine that if I divide my science images with this flat here, then I'll be pulling as little information out as possible. I'll only be correcting for small variations, the same variations as before, but the variations, the data I'll be pulling out is practically none, because dividing by 1 is, well, close. It's 1. It's the same value as before. So now we have the bias, the flat, and the dark images in our disposal. So now we want to go ahead and look at this R image here. Now, as you can see, this is how the file looks when you get it from iTelescope, and unfortunately this file format, PyRAF or IRAF, cannot recognize it because there is a space here. I hate it when people does that. But anyway, I found a very clever way to easily take care of this. So we'll go to the directory where we have the data. Here. And then we'll be use something called rename. Oh, sorry. And I actually know very little regular expressions, but I've learned that this Perl regular expression take care of what's going on. I'll first be writing it and then I'll explain what it does. Sort of. So first the command, and let's just say we want to put an n in here. Now this value here just output the results, but just doesn't change anything. So this S means substitute. So I'm telling the rename command to substitute any space with a bar, and this G I'm not sure what stands for, but it works anyway. And then of course what I want to change is all the wildcard.fit files. So let's see what happens. Let's just take one. It has renamed this to there. You see, this space here has been substituted with a bar, and that is what we wanted to do, because then this file is in one part. If we were to use this file name here, then IRAF would think that this would be the file and this would be some sort of change in parameters. Now that of course wouldn't work. So let's change the n to nv, /v, and now it should be changed. Take a look. Yeah, it is. So now we can go ahead. So what is it that we want to do here? We want to correct this for bias, dark, and flat. So again, we'll open ccd-proc, and we'll just change to wildcard.fit, output it. No, sorry. We'll make a list. So we'll say files.wildcard.fit and output it into input. And now I want to use this little Python script that I made. You can see it here. Let's go back and check how many files do we have. We have Well, we'll check it in a simple way. We have the input file, then we'll use this command vc.l input, and we have 18. So we'll go back, and then we'll change the Python script I created. So this Python script can easily be explained. This is something I want to import, just to be sure. Then you'll input the number of files. Can't even remember how many we had. We had 18. So we'll put in 18. The name of the file, well, it's red, so we'll put an R. Then we'll open a text file to write into, and then I've made this suffix command here. At start it will be slash bar 2 zeros. So we'll say that for I in range, this is just a normal loop, to n, there's 18. If we have this that is less than 8 or more than 8 or less than 100, then the suffix will be changed. And if there are more than 98, the suffix will be changed to this. We could actually change this to 98 and nothing would happen. But so this basically does that. If we hadn't had this little if section in here, you'll just get 2 zeros everywhere in the file name. But because we want to have 001, then 010, then we'll say that if it's greater than this, because I started 1, you should remember that, here, we'll say that if it gets larger than 8, which is actually 9, because we get a +1 here, then we'll substitute this here with this. And if we have more than 98, because that is actually number 99, then we'll just substitute it with this, so we get no zeros. So let's try to run it and see what happens. We just write Python, create output, and wait. Now, of course, while this is running, and it shouldn't take that long time, I am using Linux. I'm using Kubuntu, which is just Ubuntu Linux with a KDE desktop instead of the GNOME desktop. But basically you can run Python scripts and IRAF PyRAF on any platform you can find it for. I find Linux to be the best, but it's up to you. Now I've outputted this back to this. I've outputted to a file called output. Let's take a look. So we have R001 up to 9, and then you can see this is what this did. If I hadn't put these if commands or if statement in, then it will say 0010 and it'll look ugly. It's all there is to it. And this is the file name. This is a little Python script I used because IRAF likes to have these output input files catalog which you can correct with. So we'll move this output to the R and go back to PyRAF. So now we have an input file, an output file, and a flat directory. And this is, of course, as I said, because there are no raw flats. This is the master flat we have here, which we'll be correcting for. So we'll be taking epath ccd proc, move it a little away, and then we'll say we'll have the input in. This is okay, but we'll have to output it to the output because we don't want this ugly long file name and we want to correct the numbers. CCD type none, max cache none, and then this will be okay. And if you, in your case, you would leave this as it is and then just input the flat in here, but because we have corrected for dark 1 and this is 2-bin, you'll have to use the bias 2-bin, the dark, 2 bin, and of course the flat in here in the R directory is in itself 2 bin. Now we should be able to correct. And this of course will also take a little time. Now, when you do science images, you will probably be using something called dither. And dither is that when you point your telescope at somewhere in the sky, you'll usually be using some form of guiding. A camera that keeps an eye on a star and makes sure that the star doesn't move too much in the frame, and if it does, it will send correction informations to the telescope in order to be on the same place. This will give you nice round stars instead of star trails or something like that. But when you dither, you actually tell the telescope to move a little, reacquire the focus, the guide star, and then keep on guiding. Now, this is because if you want to correct for other artifacts on your image, then if you move the telescope around, not a lot, but a little, typically you use a couple of arcseconds movement, then the image itself will change position on the CCD, but the errors on the CCD will be somewhat the same place. Now, of course, when you combine this, you'll have to correct for this, and I'll show you what happens if we don't correct for it. So we have these temporaries that is corrected for bias, dark and flat, and let's just say in combine we'll use here, and as you can see, I've already taken care of, because I'll be creating another section of temporary files called temp2 with something called imalign. But let's just, for the sake of argument, show what happens if we use these temporaries here. I'll be using median combining sigma clip this time, where I've set the sigma to 4. I've still set the R noise and the gain, but I'll not be using this here. And just set execute and let it combine. So let's try to display this temp3. Let's zoom in a bit. Now you can see this actually looks like there's a lot of star trails, but in reality it's because all of these stars have moved a little on the image. So what we want to do is correct for this. Now I know that there are programs out there that can do this fully automatically for you. Programs like MaximDL or whatever they're called can do this. Just say correct, you align according to the stars, and then it will be doing it for you. But I actually find that IRAF, in many respects, if you're not using color CCDs, it does a better job. Now, this of course involves that you have to do a lot of handwork yourself. You have to actually correct, you have to provide information to IRAF how these stars approximately is moving. So I'll show you how to do that. Now, because the object is around here, it'll be a good idea to use stars that are somewhere in this approximate position. Now, when you have to correct for these shifts, I'll have chosen to use this star. I'll tell you later why, but the main idea is that this is sort of a special configuration that is easily recognizable, but you can do whatever you want. So I'll instead use here something called, let's just check, I don't have a log file, no. I'll be using a command called imexam. Now I won't be using this parameter here. I'll just show you that you need to set this at standard. This is not set, this output.log, but you want to output it to a file. I've called it output.log, but you can call it whatever you want. Just say save and quit. Now we want to do imexam on let's take a look at the parameters for imalign. So let's see what we have here. We have the input. Now we have to provide a reference image where the stars are. We have to provide some coordinates from what stars you want to try to align for. You have to output it somewhere, and you have to input some shifts. Now you can choose not to do this. Then we'll be using this big box parameter here in order to try to figure out what the shifts are. You can use this probably if the shifts or the dither, as we have used here, are not very great. But if the shifts are too great, the program, the task will get confused and probably will end in an error. So to be sure, the best thing is to use set these initial shifts. I'll show you how to do that. But first let's check the reference image and set the coordinated files. So we'll use imexam, and we'll just use the first file as the reference image and set it to screen 1. So here we are. Remember to click on DS9, and then you can see the cursor has changed to this little funny thing here. Now what I want you to look out for is that when I press the A key, something pops up here, and I'll tell you about what it is later, but right now let's just take a look. Yeah. And you'll do this with all the stars you want to use as reference stars. Remember, you should probably use somewhat bright stars. It's definitely sure that if you use stars that imexamine tells you here that some Moffat didn't converge this here, then you have chosen the wrong set of stars, the wrong star. I'll check this and probably this and maybe this. Sorry. And then I'll press Q. Let's just take a look that we don't have any. Doesn't seem that we have any that goes again. So this gives you a column and a line, some coordinates, some R value, radius, magnitude, flux, sky background, where the peak is, how high the peak is, the ellipticity, the position angle, beta, which I unfortunately cannot remember what it is. Then you have 3 sets of trying to where the program tried to fit some curve, some point spread function to this star. You have an enclosed, a Moffat, and a direct. Now, if you wanted to find out what your full width half medium value is, actually you're seeing, then you'll take this number, probably all of these, and take a mean value, and then you would multiply this with your pixel to arcsecond values, arcsecond to pixel values, and then you'll get your full width half medium in full width half at maximum in arcseconds would somewhat be your seeing. Now we'll be using these coordinates here. So we'll go to the R directory here, and then we'll edit this output.log file. We'll be doing this 2 times, but with different purposes. So we'll be removing this, Now these two numbers here are what we are interested in. They are of course go again here, but we'll only need them once. So we'll delete all these other values. Of course, the more files you have, or the longer this will take. Not this particular part, but the overall time. Now this is what we'll use as reference stars. So we'll call this file chords and delete the rest. And then close this window. Alright, so now we have the chords in place. Now we want to do something to find the initial shifts for all these images. Now you can do this in various ways to do. There are various ways to do this. You can use DS9 to plug out the star yourself on every image and then divide the numbers, or sorry, subtract numbers. But I have found that the best way to do that, you can also use a task called DAO find, DAO find. It will find all the stars in the image, and then you'll just be able to, you have to be able to select the correct stars. Now, of course, with these many stars in your image, it could be pretty hard to find the correct ones in order to subtract the correct ones from each other. So I will be using the examine to do this, but I'll be doing it in a slightly different way. So I'll create some files, a file directory with these, let's just take a look. Files, I'll be using temp1.fits, and I'll be outputting this to an IRAF script, which I will call findparse.co. Here you go. And then we'll edit this findparse.co. The first we want to do is take this temp1 and replace it with imexam. As you can see, my program already knows what I want to do. Sorry. There you go. And then temp1, say replace. So, and then because we want to put an 1 after here in order to show it in the same screen, we could also put 2, 3, 4, whatever we want to do, but in order to change it fast, then I'll just say .fits and change it with .fits1, as you can see here, in place, and then save and exit. Now we have made an IRAF script, and here's the beauty part. I'll just write CL pipe into, and then this find parse CL. And as you can see, the program automated IRAF or PyRAF automatically starts the task with the correct image. And then I'll check this star here. Press A once, and then Q. A1, Q, find the star, A, Q, find the star, A, Q, A, Q, and I'll be doing this with all the stars, or with this star in all the images. And as you will see in a little bit, the task sequence of this sequence will automatically start when we haven't got any more images of stars, or any more images to do this with. Here we go. So now we have this in an output.log, and we'll gedit the output.log again, and remind you, we still have this part up here. We'll just remove it. Now we have this part here, and the best way to get rid of this, because again we are only interested in these numbers, is to search and replace just to make sure that I do it in the right way. So here you go, and replace with so. Now we remove this. So what we'll be doing now is removing all information except for these two numbers in every part of our calculation. So we'll be doing it like this. Remember to not remove any information that you want, because then you have to start over. And this was actually the part where I said that, of course, if you have more files, then you have more positioning of stars, and then this reduction of your data file or your position file will take longer. There you go. And I will call this file positions. Here we are. Now, like I said before, you could be using Python or whatever program you want to use. I'll be using MATLAB. So what I will show you is how I do it in MATLAB, but the basic way to do it is sort of the same, but you probably have to script the thing yourself. But let's go to MATLAB, and then we'll go into the correct directory, which was our R directory. We have our position data file here, which we'll open, say import data. We have this. Now I have made the commands in advance, so I'll be using a matrix, but you can do it in any way you want. You can also use these two as separate variables and then subtract the values in the correct order, but I'll be doing it like this. Open this in a matrix, or whatever you call it, a 2 times 18 array or whatever. It's basically the same. Import data. So I have done this before, of course. So I have the new positions here, and as you can see, the old calculations I made was in a 114 by 2 double. This is only an 18 by 2. This took a longer time, I suppose you can imagine. Down here, this is the command I'll be using to calculate this. So my new variable will be, or my new array will be called new pos. I will have these brackets here will indicate that I'm creating a new array or a matrix. And what I want to do, because the first part of our, let's just open them. The first part up here was from our reference image. So of course the initial guess for the shift for the reference image will be none. There should be no shift in the reference image, because if you compare the reference with itself, the shift should be none. So this is what we have here. So the basic part is that you check the reference image, position X and Y, and subtract the image you want to correct, X and Y respectively. So reference minus check image, reference minus check image. Now because this is in arrays, this is 1 by 1 and 1 by 2, because we have numbers by 2. And then this means all the numbers in these two arrays. And let's press enter. And you can see here, of course, the reference is 0. And then you get the guesses for the shifts here. Now, this is the way I do it. So I'll just take these numbers here, press copy, and then go back to my PyRAF image, and then go to my terminal, my other terminal, and say gedit, put these in, and then save as, check the directory is correct. I'll call these shifts. Here we go. So now we'll go into the task called emalign. Here we go. So we have temp1 up here, that's correct. Our reference image, it will be in the R directory. Let's go back, R here. And then the reference image we chose was this, temp1. Our coordinate was quartz. Our output, it looks a little strange, but you can do it like this, will be temp2. And our shifts was here. Now this box size I've set to 8. Now I'll show you a little bit what this does, but I'll try to explain it right here. This little box size here determines the size of the small centering box. So this should be small enough that if we take this star, it wouldn't be able to take any other stars around here. So but if the shifts are too great, if your initial guess are way off, then the box should be able to find it. If the shifts are way off and ends up out here, then it will probably say that it can't find the star. So let's try to run it, and I'll explain what goes on. These are the parameters you don't have to change. You can change the number of iterations you want to use, but tolerance should be 0, and the max shift should actually be indefinite unless you are absolutely sure what the maximum shift should be. Now I have set the shift image parameter and the trim image parameters to 0, so we'll just get the results, but we'll not change anything. And let's try to run it. So let's see how many we got. We got 9 stars all the way down. That's good. And we can look here at the errors, that they are relatively small. That is also good. Now I'll show you what this box size is. If I set it to 3, for example, let's see what happens. It can still find the star. So let's set it to 1. See, now it couldn't find anything, of course. Let's set it to 1.5 and see what happens. Still nothing. So that's the problem here. It should be of course an integer. Let's set it to 2. Now the thing is, as you can see here, that I'll set it back to 8 and then run it. If you had a lot of stars here and there was a little shift that you haven't accounted for, something like that, then you'll probably lose some stars here. Now what you want to do is sort of what you call it, up to yourself, your gut feeling. If you lose a lot of stars and have big arrows in here, these in the parentheses are errors, then you'll probably want to look at your, first try to change your box size, and if that doesn't help, if you get more stars but still get large errors, then you'll probably want to check your shifts file in order to get to see if that's good enough. If you use this method by getting the centroid of the stars using imexam in both checking setting the coordinates for the reference file, and then in order to set the shifting of the images, then you should be good to go. And as you can see here, it's actually okay. And the 114 I did before gave also small errors, and it gave a good image. So right now I will be setting shift image and trim image to yes, trim images. But if I got large errors, then I wanted to check something in here, the shifts or the box size. Now the big box here is only used if you don't set the shifts. Like I said before, it'll try to first find the star. Is there a star inside here? And then use this small bug size in order to find the exact positions of the stars you're checking for. But in this case, I'll say in most cases, if not all cases, it's best to set this initial shift file. Even though if you had a lot of files, a lot of data files, it will mean that it will take a lot of time for you to do it. But do the work and your result will be better. So what the trimming does is that, of course, as you move the images around, you'll get different parts of the sky at the edges out here. But in order to be sure that what you have in one image or in all of images is the same, then it will trim the images in order to get only what you have in all of the images. So it's sort of like an advanced form of cropping it does. So now we have, let's take a look, we have these temp2 here. And we also have this temp3 that I'll be deleting. Delete. Now let's display temp3 fits into, just to show the difference. And then delete temp3. And then go back to imbar, edit the parameters in combine. Now I'll be changing this to 2, but leave all the things, all the parameters that we have at the same, and say execute. As you can see here, we are scaling in order to get the mean. So let's say display temp3 that fits in 1, and let's take a look. Now let's compare. I'll just match the frames according to the image, and then I'll be showing the buttons. Go to frame, and then I will say, let's say the blink interval to 2 seconds, and say blink. The difference is definitely noticeable. So this is what ImaLine does. It aligns your images in order to combine them to get a good result, and I would certainly say that this is a good result. Now, the reason why I choose this to call it temp3 is that I usually want to run something called Laplacian cosmic correction on it. I won't be showing you this here, but oh, what the hell. Let's just take a look at how you do it. We'll go into epar.lacos.im. So what this will be doing is to give you an image that is corrected for, as best as you can do it, for cosmic rays or whatever that is. But the thing is that you have to be careful about these sigma clipping and sigma fractions and object limiting values, but because if you don't, then we'll show how it goes here. I'll not be correcting anything if it goes wrong, but if you don't set them correct, then you could end up that the task will not converge but keep finding cosmic rays. And also if you have images that are not very well aligned, or that you have some lot of small specks errors around on the image that hasn't been corrected for, then you can end up doing the same. But let's see how it goes and how long it takes. One more thing I should mention about this Lacos is that you have to find it yourself. You have to find it and install it yourself. But if you go to go to and search for Laplacian cosmic. Then you'll get this LA cosmic, and you have to download 2 scripts for IRAF. You can also use them for Python, but I think that IRAF is the best ones, and you have to install them in your IRAF directory and put it in something called userlogin.cl at your IRAF directory. You can find more information on this on the net, and if you want to, I can make a quick video on how to do it. But let's run this Lakers for image. Now, when you do this, I suppose there is an actual way that you can find out how to set these sigma limits and values correctly, but I must admit I just try to guesstimate the values, and if my program does not converge against 0, then I will change the parameters. As you can see here, I think it actually converges quite nicely and should give us 0 within this iteration or the next. There we go. So let's try to look what we have. One other thing that you should notice is that if you haven't set the values in Lakers Laplacian cosmic correction correctly, then it could actually begin to attack your stars, and then you'll see black circles or streaks or something like that in these stars, which is obviously not good. Now, this concludes this tutorial on how to reduce your images using IRAF. It takes somewhat long time, but I definitely think it's worth it. And the next video I'll be doing will probably be how to reduce spectroscopic data from telescopes, which I might split up in 2 parts because it takes a lot longer time than it takes to reduce data from just images. When you have done this, if I did this on all the images, red, green, blue and luminance, then I could go back into, I could combine them with an RGB frame here using the red, green and blue, or I could go into a program like MaximDL on Windows or something like that, and then combine a real luminance LRGB image. But this I will obviously not be doing here. So bye bye, hope you can use this video for something.